So, one of the most transformational trends in the electric power industry today has been the declining cost of solar. So, if we were going to think about maybe the two most important trends from a technological standpoint, from a market standpoint in the electric power industry, so we're not going to necessarily count regulations, although those have been extremely important. You would think about natural gas prices being low as something that has contributed to widespread retirement of coal-fired power plants and a much larger share of natural gas generation in the power mix and the construction of a lot of new natural gas power plants, for better or worse, as well as low electricity prices. The other really has been the declining cost of solar, and how that's changing the marketplace today is in some ways less important and less impressive than the way that it promises to continue to change the market in the future. So I think the declining cost of solar has, in some ways, put utilities and the electric power industry in a larger sense on notice, and is reason for a lot of hope. For some people, if you're a proponent of renewable energy and reducing greenhouse gas emissions, but it also um, could potentially have a destabilizing effect for incumbent utilities. And part of that has to do with the potential role of solar as a distributed source of generation, a customer-owned source of generation. That's something that we'll talk about more today, but also in future lectures. So one of the terms that's used to describe the decline in the cost of solar is Swanson's law. And so this is actually, it's not a law. It's sort of an observation in the price of solar over recent years, and it's similar to historical observations of the declining cost of computational power in computers, which we refer to as Moore's law. So Swanson's law is this observation that the price of solar photovoltaic modules tends to drop 20% for every doubling of cumulative shipped volume. And so we can compare that to what we saw throughout the 70s, 80s, 90s, and 2000s with regard to the transistor count in computer chips. So computer chips are getting faster and faster, or at least they have historically. And we see something kind of similar with the cost of solar panels for every increase in volume of shipped. We get a decrease in the actual price. So one of the reasons why the comparison between solar, the cost of solar panels, and the transistor count in computer chips is that solar power is in some ways better thought of as a technology whose cost over time is going to decline, similar to the way cell phones get better and better, and computers get better and better, and as a result, your money goes further when you're the type of computer that you could buy for um, $2,000 5 years ago, you could buy for much cheaper today. And so I think that it's a useful analogy because of the cost trajectory that we've seen with solar. Now, extrapolating that too far into the future may be somewhat problematic. Um, but I think there certainly is a lot of optimism that the cost of solar is going to continue to decline for a variety of reasons, right? So at least historically, we've seen declining costs of solar because of fundamental technological advancements, manufacturing improvements, industry restructuring. Some of that might mean consolidation. We'll talk about that a little bit at the end. And economies of scale. So the more of something you produce, the better able you are to spread the fixed costs associated with that production process over more and more individual units sold. And so the average price of the good declines. And then also better financing options. You could imagine that the first solar power business, panel manufacturer or solar panel developer, was sort of seen as a risky proposition by lenders, so that when they wanted to go out and borrow money in order to build the infrastructure they needed to be, commercially active, they were charged a higher interest rate. And so, what you should remember from the beginning of the class about financing infrastructure is that the higher the interest that you pay, the more interest you're going to pay over the lifetime of the loan, and that translates to a higher overall cost. So simply by having successful, solar businesses, whether again that's on the panel manufacturers or solar power developers, lenders are becoming more comfortable, and some policy has been designed directly to provide access to better financing options for solar developers as well. So if we look at the levelized cost of electricity for solar, again, that's sort of the break-even cost of electricity that a solar power, a solar farm would have to sell its electricity for in order to break even over its lifetime. There's a kind of a big range. On the low end, it's quite low and is competitive with onshore wind and combined cycle natural gas. But there's a big range for solar here because depending on where you build the solar panel, the levelized cost of electricity is going to be higher or lower. And that doesn't mean that the capital cost of solar is higher or lower, but it does mean the amount of electricity you generate from the solar panel could vary considerably. So if you have, the way we define levelized cost of electricity is $1 per megawatt hour amount, where the dollars in the numerator on top the lifetime cost of building and operating the power plant. So this in this case, it would mostly be the capital cost of developing the solar farm and then paying those off over a long period of time. In the denominator, it's the amount of electricity that you're selling in megawatt hours over the lifetime of the project. So if you're building a solar farm in two different places, and in the numerator you're having the same capital cost, the only thing that can change the levelized cost of electricity is the value in the denominator. So how much electricity you're producing over the plant's lifetime. So if you build that same plant in New Mexico or Arizona, where you get a lot of incoming solar insolation, and you build another one in Alaska where you don't get that much, the value in the denominators are going to be a lot different. And so you're going to get a lower cost, levelized cost of electricity in a place like New Mexico or Arizona, where you're producing more solar power over the plant's lifetime than you would in a place like Alaska. So as the cost of solar has declined, we've seen a dramatic increase in installed capacity. And so that's what this figure shows. You have the price of solar panels per watt declining in orange, and then global solar panel installations increasing in blue. Now, that's really impressive and it's really encouraging, but this is a figure I showed last time, and it's useful to keep this in perspective. This is the 2017 U.S. generation mix. This is the combination of installed capacity from which we derive all the electricity that we use in the United States. And so we saw last time that there's been explosive growth in wind power, and we're seeing this time that there's been really explosive growth in solar power as well, especially PV. Now, what that has meant over the last 15 years is that we're up to about 8% of our total generation mix that's taken up by wind and solar. We still have a grid that is dominated by these traditional incumbent players of natural gas generation, which is increasing, largely due to the lower cost of natural gas from fracking, and coal, which is decreasing for a variety of reasons. Part of that's regulatory, part of that's economics, and nuclear, which is also decreasing, again, partly because of increased regulations, and a big part of that has been a low market price of electricity.